Hey, Mr. Ensmeyer again, here with our second recursion video. This time I'm going to do one of your favorite problems, the good old digit splitter. We're going to do it, though, using recursion, just to show you how that works. So if I come up here, let me make a little integer function. Eventually we're going to add the digits together. I'm going to send in a number, and I'm going to add up all the digits in that number. So like if I send in 1, 2, 3, 123, it's going to give me 6 because 1 plus 2 plus 3 is 6. Down here, if I see out add digits, and again, just put in some kind of number there, and then of course let me declare that and enter that number. How in the world are we going to do this using recursion? Well, we come on down here, little comments, 123. Oh boy. So what we're going to do? Well, we know from our past experience that we're going to do divide, we're going to do mod. We're in base 10, so everything in our number system is based off of powers of 10. If I take 123 divided by 10, I get 12.3. If you don't believe me, you can do it on your own. You get 12.3. If you're going to do the integer version of that, you just get 12. Which means when you take 123 divided by 10 as integers, you get 12. But when you take 123 mod 10, you get the 3. You get the tens place, you get the ones place. And so here's where the recursion comes in. Because I'm going to take the digits off the right side, bit by bit by bit. And if you think about it, all I need to do this process over again is, okay, I pulled off the 3, and now the next number is 12. So 12 divided by 10 is 1, with a remainder of 2. And then 1 divided by 10 is 0, with a remainder of 1. So where is my sum? My sum, boink, 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 3, 2, 1 is 6. Our base case is when there's nothing left to divide. So we have two cases. We have the recursive case, we have the base case. Let's start with that. Recursive case, base case. So we have our number, and we know that if our number, when we divide by 10 and get a remainder, is it the remainder? No. See, the base case and the recursive case in this case are going to be a little bit different. They're not based, oh, this is horrible. They're not based off the same thing. One's based off of division, the other one's based off of remainder, which technically is division, but you get what I'm saying. One's off of the slash, one's off of the mod. So, if I do this, when I divide it, is there anything left? Well, what's left? What do I return? Do I return 0? Do I return the number? I don't know. Let's find out. And then if the number divided by 10 is greater than 0, what do we return then? We return the number plus the number mod 10, perhaps, because this is our remainder. So there's our 3. But do we return the number? Do we return 123? No. Remember, the recursive case must call a fresh copy of the function. So I don't return the number plus. I return this plus. But I don't return the number. I return the number divided by 10 plus the remainder. Look that over for a second. Think about the number I have at the bottom. I sent in 123. So 123 divided by 10, that is still above 0. It gives me 12. So I return a fresh call to the copy of the function plus the 3. So in memory, stored up here somewhere, there's 3. When I come down here, again, when there's nothing left, I return nothing. There's nothing more to do. And so I have this and I have this. Well, I don't want to do them separately. I want to do an else. I want to have one case, and then if it's not that, it's the other case. Let's give that a shot. Again, we're looking for 6 when we send in 123. Close. It's not quite right. The answer is why. Should we return nothing in that last step? This is the nothing. But, if you go back through our problem, when you send in 123, there's the 3 right here on the first step. This is add digits 12. So you do that. Is 12 divided by 10 above 0? It sure is. So split off the 2 and do a fresh copy with 12, which 12 divided by 10 is 1. So now it does this one. So it has 3 and 2 held in memory. But it never got to 1. It never got to this the final digit, the leftmost digit. So I don't return 0. I don't always have to return 0, return 1. I can still return something in the base case as long as it's not a copy of the function again, because that defeats the purpose. The base case should return something that ends the recursion. So what do I put here? Well, I put here what I need to put. I put that final digit. 1 mod 10 is going to give me 1. 1 divided by 10 is 0 with the remainder of 1. So now 123 gives me 6. And the nice part about this function is it works with any size, of course, as long as it's within the range of integers. It works with any size integer. I don't have to worry about how many digits are there. It's just going to split them off from the right to the left, one by one. And again, the way it does it is the sum of the numbers from 1 to 6, add 7, would equal the sum of the digits from 1 to 7. Take any subset of these numbers, and it's kind of like factorial, except you're adding in this case. 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, the total of that would equal 5 plus the total of 1, 2, 3, 4. 6 would equal the total of 1, 2, 3, 4, 5 plus 6. That's what you do when you do recursion, is you break the problem down into smaller and smaller segments. And so, one last time, the recursive case is when you keep going, you find a smaller copy of the problem that you can call fresh in your function. So there's no loop involved, the recursion is the loop. And then you add on, or multiply or subtract or whatever, it doesn't have to be adding, but this is held in memory somewhere. It's on the stack, and you'll learn about that later. This is a little bit more advanced than we need to go into for right now. I just want to show you how this works. You're not going to have to model these things per se, as long as you just can kind of walk through them. So again, take a look at that, let it sink in, let it become part of you. Get it into your soul. Recursion. Thanks again. Take care.